Welcome everyone. Today we are going to talk about consistent hashing algorithm in terms of distributed systems. On top of that, we are going to implement it using the .NET. Demo will be in the end, so let's go. But before talking about the consistent hashing, we should talk about distributed systems a little bit to give you a little bit of context. So, distributed system is just a regular system that serves some purpose but consists of multiple machines, multiple servers connected into the same network, and that's basically it. Why you might need a distributed system? Why it's not enough to have just one machine serving all the requests? The answer is pretty simple, and all of you most probably know it already. It is because of high load. If your machine cannot serve the particular amount of requests, you should spread those requests between different machines. So let's say you have a server that can serve, I don't know, 10k requests per second, but actually you have 100k requests per second. And what you can do, you can scale horizontally, adding 9 more servers, each of which can handle 10,000 requests per second. And then you need to redesign and re-architect everything to achieve some level of consistency, to achieve some level of reliability and stuff like that. But let's talk about the spreading the load in terms of data first, not in terms of requests. So let's say you have some database or cache and you have too many requests per second and too many data in your data store. So your server actually don't have enough memory to handle all the data that users want to store in your database or cache, whatever. So in that case, you need to split your data somehow and put some amount of your data to another server, and now your users are talking to two different servers. The process that I have explained so far is called partitioning. Partitioning is a technique that splits data among machines so that each machine is responsible for handling a subset of data. Okay, so good so far, but how your clients actually can decide to which machine they should go to get the data? You should answer this question before you start designing your partitioning. Mainly there are two main partitioning approaches. First one is partitioning by key range and another one is partitioning by hash of the key. Most of the databases and caches came into the conclusion that it is better to partition by hash of key, even though some of them support partitioning by key range still, that's okay. And we are going to talk about partitioning by hash of the key today. And to put it into more native domain, we are going to talk about a distributed cache. The good example is Redis. Unfortunately, Redis uses different technique than consistent hashing. Consistent hashing is used by Dynamo, Cassandra, React, and also it seems from MongoDB documentation, it is used in MongoDB as well. There might be different details that make those algorithms different from each other, but the main idea is the same. So let's jump into idea itself. First, let's consider the naive approach that can come to your mind straight away. So the naive approach would be the following. Let's say you have 4 servers, 4 machines, and you have some range of possible hash values, let's say from 0 to 1 million, I don't know, your hash function. And you need to distribute all those million values into 4 servers. The naive approach that actually pretty much used in local hash tables that you're using when you're writing your code as a data structure is to use modulo operation. Let's say you have 4 servers, you have some value, and you perform modulo operation on this value. Value is actually the hash of the key. And you get the answer to what machine the value actually should go. So you can see that we have possible hashes. We don't talk about the keys. This doesn't matter for us. We are talking about hashes 1, 4, 7, 10, 12, etc. We perform modulo operation, and that's how those hash keys will be distributed in such algorithm. So 4, 12, 16 come to 0 server, 1 goes to first one, 10 goes to second one, and 7 and 15 goes to third one. That's okay, but we are talking about distributed cache when one node of your distributed cache can just go down. You might get a hotspot where some of the requests come to the single machine and you need to redistribute your load and to add new node to your cluster actually. So let's take a look what happens if you add one more node to your cluster. Let's say the last one was third, now we added fourth node. What actually will happen with all previous data that you had? I marked as a blue all the values that should come from one machine to another machine, which requires you to send a HTTP request to one machine, get the value, send another HTTP request to another machine, got the confirmation, delete the value from the previous one, or you might not delete it, but anyway. So as you can see, now module operation doesn't work well because you need to redistribute almost all values except the one. All other values go to different servers, which makes it bad because if this machine is overloaded anyway, you are adding new machine to your cluster and you adding the big load of shuffling your keys here and there along with the requests that are coming from users. So that's not that great. And this is why we need consistent hashing. Usually consistent hashing algorithm has two main representations. Let's say you have your range of possible hash values starting from 0, ending of max value that your hash function can produce. In my case, I used the Jenkins algorithm that produces maximum 32-bit value. So it's in .NET, it's just in 32 max value. Usually consistent hashing algorithm represented using the ring, where you have 360 degrees and you put all your values and nodes into this ring. For me, it was always not clean how you map degree to particular hash value, or vice versa, how you put your hash value into particular degree, how do you calculate it in an efficient way and stuff like that. So actually in most of the implementations you don't work with the degrees, you are working with hash values. To put it simply, now your hash ring does not end with 360 value, but it ends with maximum value of your hash function. In our case, it's int maximum because it's the maximum value that can produce my hash function. Not mine, but like Jenkins. And any value that you're getting from the hash function, any hash, you put into this circle. Working with circle wasn't that convenient to me, this mapping of degrees and stuff like that. On top of that, you're not working with degrees usually, you're working with hash values itself, and your maximum is int max. So I changed to number line representation, which looks like this. Pretty much is the same circle, you just need to tie the int max and 0, but for me it is easier for understanding to use it as number line. In this number line you put all your hash values into this line and you put your nodes, aka servers, on this line as well. You can do it manually or you can just calculate, I don't know, URL of the server and get the hash value of this URL and put it into the number line. How the actual algorithm works. We have some invariants that we need to keep to make this algorithm work. Okay, you have some amount of nodes on your numbers line and you keep the invariant that all possible values that are located before the node inclusively are belong to this node. So in this case 3, 4 and 6 belong to first orange node. And 10, 11, 13 belong to this blue node. And since after the blue node we have only maximum value, we shift those value to nearest node as a circle representation. So in that case we have 3, 4, 6 here, and backwards we are putting all the latest values to this orange node as well, because they are kind of before the orange node. but after the blue one. At some point, when you need to add one more node, it's not a problem because you can put your new node in the middle between the two existing nodes and just shift the traffic from the next node. Half of the traffic, half of the data basically. So let's say you have two nodes. One node is located on value 7, hash value 7. Another node is located on hash value 14. You're putting midpoint between the nodes, but actually you don't split them by the range. You split them by the middle value itself, because you can see that the distribution of the load might be the following. So you have 6 values for the right half and only 2 values on the left half. And it's not what you would like to achieve. You would like to do it as evenly as possible. So you choose your midpoint as the middle hash value that node contains. In that case, since our overall amount of values are 8, 1, 2, 3, 4, 5, 6, 7, 8, we need to put 8 divided by 2 is 4th. 4th element will be the place for the new node. We put the new node on the 4th element. Keep in mind that the values are still belong to the blue node. And we just transfer half of those values from blue node to new orange node. And by doing that, we don't affect any other node in the cluster. We might have 100 more nodes that will serve their traffic independently, and we are shuffling the items between only 2 nodes. And that's the beauty of this algorithm, because in case of modulo, we will shuffle all the values between all the nodes. And that's bad about this algorithm. So we moved half of the values to orange node again, or yellow node, I don't know. And now 4 values can be served from this 11th node, and 4 another values can continue be served from 14th node. And that's it. Actually, we spread this one evenly. And now 14th node has double less data and double less requests than it has before. So that's basically the algorithm. It's pretty simple. Now the implementation. So while I was architecting this one, I was trying to do the best approaches from data-intensive applications and based on my teeny and small experience. So I came up with something like that. It turned out that this architecture is really similar to MongoDB cluster architecture. I found it out when I was writing my article regarding the consistent hashing, because firstly I did the implementation, then I wrote the article. So that was funny. So in this architecture we have our client. Basically this is client application. We have load balancer that is responsible for directing the particular client request to particular child node. Child node is our single distributed cache node that is serving some range of the consistent hashing ring. Particularly, each child node is one circle in this diagram, so it serves only some subset of data. Load balancers are keeping the numbers line or this ring in the memory, because they should know somehow, if they got 11, they should know somehow how to get to 14th node here, right? Why we don't have single load balancer? Because this brings the problem of consistency. You need to keep your circle consistent between the load balancers. This is because load balancer can fail, and in that case it is single point of failure, and your client cannot do anything. It cannot get the data, it cannot set the data to your child nodes and basically to your distributed cache. So that's why I keep the different load balancers. It provides some consistency problems. So in that case, it's eventual consistency guarantee. But I think it's good enough in our case. Reliability comes first. Okay, now we have multiple child nodes assigned different numbers line range. And we have master server. or master service, or just master, I don't know. So this is not the service I like, because it has really a lot of dependency. It is the single service, so we don't have two masters because of consistency and race conditions problems that we can have. And master actually is updating the circle in the load balancers. So master actually talks to child nodes, and child nodes are talking to master, either directly or indirectly, using, for example, some messaging queue or something like that. But in our simplified version, we will just directly talk through the HTTP protocol. So once the child node is full, let's say we on that point, when we would like to rebalance 14th node because it has 8 elements, and let's say in our case 8 elements is the highest bound that node can handle, it throws notification to master that please rebalance me, and then master starts rebalancing. Master can spin new node. We will do that using the process API, but actually it should be done, I think it can be and it should be done using some Kubernetes API whenever you have all the containers and you just up another one container using the Kubernetes API, update your load balancers, and that's it. But in our case, we are spinning new instance just by starting new process in the local machine. I will explain it during the demo. The rebalancing point is pretty tricky because it might have different problems with consistency. We will consider it during the implementation overview as well. Okay, so the demo first. On initializing point of our cluster, I'm creating 2 load balancers and 2 child nodes with those ports. Also, I have added the informational endpoints so that we can query all our cluster and understand which node contains which data. I don't have any durability mechanism, so I don't store anything into the file, database, or anything like that. I'm storing everything in the memory. It is not that expected to have a durability, at least in our simplified version. So let's start. Okay, from the logs, we can see that our machines started. We have our endpoints up. We can actually check that they are alive. We can just query it by the port. They are all localhost. They are all APIs, and meaning that we can access them via the Swagger. This is our child, and this is our child. And just for demo purpose, I can demonstrate that by port 7009 there is nothing. Okay, actually those are informational endpoints here. For example, in load balancer, we have endpoint called values, and we can see that we have only 2 nodes with those ports, their ring positions, and maximum items that they can handle. And cache items are empty right now. And those load balancers are pretty much synchronized, so both of them have same information. Also, one more thing we are not doing with nodes in general, but we are keeping separation between physical nodes and virtual nodes, meaning that one physical node can have different virtual nodes, but in terms of our architecture, actually when we are talking about the node on the circle, the node on our hashing ring, we are talking about virtual node. So those two can be one physical server, but 2 different virtual nodes. And it can help you for pre-setup. Let's say your machine is pretty strong and it can handle 3 nodes. And another machine is pretty weak, it can handle only 1 node. So there is separation. But anytime I'm talking about node, I'm talking about a virtual node. Let's see what our master has. Master has actually access to all the nodes. So it is a little bit not good namings, I would say, but still. We have our first load balancer that has two nodes. That's it, with hashing in positions and stuff like that. And we have another load balancer with the same two child nodes, and they're empty. Okay, so now what we are going to do, we are going to use our one load balancer and start adding values into it up until we got 5 items max in one or other node. Then we will start rebalancing. Okay, and we can see that the request took a little bit longer than it is expected. We have added 7 key, and let's say what is going on in our cluster. Boom! We can see that there is one more node with port 7K10, and it is right now is handling 2 and 3 as a value. And this node got these values from the first node because of rebalancing. So this is actually it. We can keep going and we will get new nodes. I didn't implement the algorithm of removing the nodes because it's like pretty much other way around. You just need to drop the node, move one item range to the next node and stuff like that. So we will do only rebalancing in terms of adding a node. So let's start talking about the implementation. What happens actually when we rebalancing? This is the most important part here, because all consistent hashing is solving basically rebalancing problem. Let's take a look into the master, and let's take a look into the master service, which is also singleton service, and it handles the rebalancing. We are using here serializable lock, which executes everything in one thread manner. So no two concurrent rebalancing can happen, because if that happens, we can miss some consistency points. So we actually would like to do rebalancing using one thread. It takes time, yes, but rebalancing itself is time-consuming operation, so we really don't care. We are caring about the consistency here more. So what happens in the rebalancing? First of all, we have our hot virtual node, which we would like to rebalance, which exceeded the max items count. We're resolving hot physical node. Basically, it is one-to-one mapping, as I have told before. We are creating new physical node here, and we deciding from the values of hot node, we are getting first half of them. This is why we keep sorted list, because when we have sorted list, we can get the first half of the all key value pairs. Basically, we are performing this one. We have all the items and we need to get the middle point, and got only first half, the orange one. So we got this first half here. We decided the node position from this first half as a last one. So the node position should be the last one of first half, this one. We create a new virtual position, new virtual node, and we added this node to master, and also notified this new physical node that still does not have any virtual node, so it cannot serve any traffic. We are adding this virtual node into it. Now this new physical node can serve and can actually serve the requests. Then we are moving first half from the hot node, this one, to the new virtual node that we have created so far. After this one, we can serve get requests from the new node. So it now our numbers line in the master service looks like this, but in our load balancer it still looks like this. We have still two nodes in them. So for now requests are served by only 2 nodes. So we are updating all the load balancers that we have. We are notifying them that, okay, there is another new node and you should start setting and getting values from this one for this range. Meanwhile, we are doing it one by one. We can do it parallelly, but anyway, it does not provide that much guarantees. So while we are updated one load balancer, another one still has 2 nodes and this one has 3 nodes. And if user tries to get the value it sets before from this load balancer, it can go to third child node. But if it goes to this load balancer, it can go only to second child node. So there is some inconsistency, and there is a possibility that some of the requests came still to second node while they actually should go to third node, newly created, this orange one. That's why after we updated all load balancers and now all the clients are served properly, we getting first half from the hot node again, because meanwhile, while we were updating all the load balancers, some of the clients might set values that actually should belong to third node, but since load balancer is not updated, they were served by second node. So we are moving the first part to third newly created node again, so that customer that just set the new key value pair will not lost it. And now we are removing first half safely from the hot node, and that's how we rebalance. Now we have basically this picture when the new node is serving half of the items of hot node. That's basically the algorithm. You can go to my GitHub account to see the source code, actually how it is implemented. It has a lot of problems for sure, because it's really simplified version. One thing I would like to point your attention is the hacky way of creating new instance. Basically, we are spinning it using the DLL. So I just can calculate the path of my assembly of child node, of assembly of master, assembly and load balancer, whatever I want. Having this path, I can actually, using the process API, the operating system native API and C#, I can spin new process, and then how it works locally, it will go up and you can start interacting with it. So let's say we have some assembly path to child node or to load balancer, doesn't matter much. We have some port. This is the behavior, like also hacky behavior only for demo purposes, how to calculate unique port that is not used in our case. We are setting the URL by which we would like to up our instance. We are adding argument, URL as argument. We create a new process, setting assembly path, arguments, start, emulating long operation in case of, for example, Kubernetes, and we need to give the node actually time to be initialized properly as well. And now we just added the process, so then whenever everything goes down, we can just kill that process. That's basically it. Actually, it should be done using the Kubernetes API, having everything dockerized in the Docker containers. We can just spin new instance using our container orchestrator, Kubernetes, and yeah, and that's how it should work. But this is hacky way. Let it be like that. And now the tricky part here, not the tricky one, but still, is to how actually get from the hash value, let's say 11, how we can get 14th node, because it can be anything in this range, and we would like to calculate the particular node that should serve this hash value as fast as possible. So since we are keeping this in the sorted list, we also can have some balanced binary search tree, whatever. I think internally it might use binary search tree as well, but I just used this one. I think the guarantee is log of n, but I'm not sure. I can check the source code. And anytime we would like to calculate particular node, we are performing some kind of binary search. So from the sum point, let's say 10, we are using binary search to get to 14th node, because our sorted list contains only the nodes. So this binary search is implemented here. So we are cut the value by max hash value that can be. And we are doing particularly binary search algorithm, and then we're returning the node. The only one tricky thing here is whenever we got to 20 or 21, we actually should return orange node, but this is in implementation details of this method. Actually, I have some sort of unit test for this one. You can check this as well, you can run them. Okay, that's it. If you would like to have more detailed view into consistent hashing and its implementation, you can check my article and GitHub for sure with the source code of all of this. And from my side, thank you for attention and see you.